Okay, so welcome everyone. So I'm happy to see you at the next lecture, Łojasiewicz lecture, that is already traditional. And today I'm having a great honor to welcome Professor László Lovász from the Rényi Institute of Mathematics in Budapest. And my welcome is on behalf of the authorities of the Jagiellonian universities for a few words about our today's lecturer, about his research work and about his achievements. I ask Professor Zbigniew Płocki.
Okay, so I'm not sure if I say too much about your research work, but László Lovász is a world-famous specialist in combinatorics and graph theory. So from what I heard, he has been already a prodigy as a child, and I found out he was actually first a silver medalist at the International Mathematical Olympiad at, I think, age 15, and then 3-time gold medalist. So, then his career was, well, of course, started in Budapest, and he was at the Laurent University, later at the Rényi Institute. He spent a number of years in United States at Yale University and Microsoft Research Center. László Lovász received a number of very prestigious prizes and awards. Let me mention just 3 of them. So that's a personal selection, if you will. One is a Wolf Prize, a very prestigious one given in Israel. The second one is a Kyoto Prize, and I'm mentioning it because Krakow has some relation to it. Namely, in the 80s, Andrzej Wajda, a famous film director, received it, and this actually started this project that is now at the bank of Vistula River, across from the Wawel Castle, is this Japanese center manga. And the third prize, 3 years ago, the Abel Prize, jointly with Avi Widgerson. But apart from his research work, he's also almost equally important his contribution, general contribution to the research community. So László, in particular, has been a president of International Mathematical Union. Among various roles, the presidents chair Fields Medal committees. So he did it for the Fields medalists in 2010. So you can check what Fields medalist this one awarded. He has also been president of the Hungarian Academy of Sciences, actually in a very complicated and difficult, politically mostly, time. And this, since we at that time did work together at some point, I actually slightly experienced that. So that was definitely, well, that was the time where the government took away the research institutes from the academy. So a very tough time indeed. And now he's a member of the ERC Council. So also a quite important role for mathematics and the research community in general. So So we are very, very grateful that you agreed to come to Krakow, and very much looking forward to your talk, and the title you can see on the screen. So please, Professor László Lovász.
Can you hear me? Yeah, I think so. So, thank you very much, first of all, for this invitation to this, well, very prestigious talk, but more to this university, this with great traditions and the fantastic history. I had a little chance last night to see the bench where Nicodim and Banach are talking, and this is really somehow moved. You will see that what I will talk about is really somehow my sort of late excursion into their work, or it's related to that. So it was most appropriate that I saw them, that Professor Blatsky showed me. Okay, so I would like to talk about this fact that it's natural to approximate the infinite with some kind of very large finite structures. That goes on everywhere. 3D graphics, numerical analysis, just the screen of this computer, it's approximated. It's supposed to be some kind of continuous image, but it's approximated by pixels. Or in algebraic topology, you have to do this approximation by Simplicial complexes, say, in a particularly appropriate way. But that's sort of the natural thing. So what about the other direction? You have something discrete and want to approximate it by continuous. Now, continuous seems to be more complicated. So why approximate a discrete object by a continuous object? And indeed, it has been unrecognized for a long time that, say, anything about a finite structure is not non-trivial. The idea is that, it's finite. You look through it and you have everything that's needed. But then for actually solving this, particularly in algorithms, it turned out that it's often a good strategy to approximate some discrete optimization problem by an appropriate linear programming problem. Linear programming relaxation is often called. There is this is sort of on the border of discrete and continuous, because linear programming is about a discrete set of conditions and extreme points, so you can understand it quite well without actually needing to know much about analysis. But semi-definite optimization is also another method where you use this kind of approximate the discrete by the continuous. Or whenever you write up a generating function, you really convert some combinatorial problem into an analytic problem. You convert certain recursions into derivatives and differential equations and so on. Or let me just mention the late Jerzy Matruszek has a book, a very nice book. It says Using the Borsuk-Ulam Theorem. And of course, you can use the Borsuk-Ulam theorem in topology, but he's not using it. He's using it in discrete mathematics. So these are, I could talk about any of these because they are all relevant things, but I would like to talk about a more direct approximation of the discrete by the continuous. And let me start with the following question. Here is a piece of steel. is it a discrete or a continuous object? Well, since we know quantum physics, or actually just modern physics, this is a finite network of atoms. And so, in principle, if you want to know anything about it, you can look at this finite network of atoms, write up how the equations link these atoms, and solve this finite set of equations. I mean, that's nonsense, of course, because this set of equations is huge. And so what an engineer does is that he considers it as a continuous object. He writes up differential equations for the density, the pressure, the temperature, a small number of other functions defined on this part of the space. And we can solve these differential equations, and we know that bridges, with a few unfortunate exceptions, but bridges do stand. So this is a valid method to approximate this huge discrete object, this piece of steel, by a continuous. We think of it as continuous. So this leads to a topic which I will not talk too much about, but I need it to motivate with it the next one. So suppose we have graphs, finite graphs, but larger and larger. And suppose as they grow, they become more and more similar in some sense. So for example, there's the sequence of complete graphs. There's not a lot of difference between a complete graph on 1,000,002 points and 1,000,007 points. They sort of not. Or very long cycles. It's difficult to distinguish them. A more interesting example, I will come back to this, is larger and larger pieces of grids. If they are very large, they are also very similar. Or hypercubes, which there should be some way of understanding the very large hypercubes, similar to the way an engineer would look at it, that it's some kind of continuous object. But what object is it? So let's start with the example of grids, because that's a very interesting example. So if you ask the audience what's the limit of this sequence of larger and larger square grids, you typically get two answers. The natural answer is, of course, it's an infinite grid. It's larger and larger, eventually it becomes infinite. If there's anybody, is there a physicist who works in statistical physics, would say, oh, no, it's a dense square. You're doing finer and finer subdivisions of the square, and eventually it becomes just a square with the interior filled in. Here is a third possible answer, and I will argue that this is a valid answer. So let's take the 1-by-1 torus. So in other words, take the unit square with the opposite edges identified. And pick some irrational number alpha, and you define a graph on this torus. You connect 2 points if either vertically or horizontally they are at distance alpha apart. So if you pick any point and you follow what it connected to, you get a countable set, which is just a grid, an infinite grid. Because of the irrationality, it never returns, so you get all different points. So what's the difference between the first and the third example? Well, if I ask you to pick a random node, a random vertex of this graph, there is no good definition of a random point of an infinite grid. countable infinite grid, because one of those unfortunate properties of probability that if you have a countable set, there is no uniform distribution on a countable set. However, there is a uniform distribution on the last example. So we could say that here we can pick a random point. Now, why would you want to pick a random point when every point looks like the same? In this example, I am not going to argue. I will show you in a minute a more interesting example. But first, let's, so this is just an informal definition, a sequence of graphs which are larger and larger and more similar. What does it mean, more and more similar? It means that there are some well-defined statistics or tests, and they are less and less distinguishable. So as you go, these tests are less and less possible to distinguish them by these tests. Then, now what can be these tests? So for example, pick a random point and look at the neighborhood. That would be or maybe neighborhood of 10 steps. And that would be a test. What distribution on these possible neighborhoods you get, and if two of these are indistinguishable. So very large grids are indistinguishable by this kind of tests, because with high probability you pick the point from the interior, and so you will not see the boundary. So you will not know how large this is once it's large enough. And this was an important definition by Benjamini and Schramm, that if these neighborhood distributions of a random node they are less and less distinguishable, then they are called locally convergent, and this is you can then study this many interesting examples of this actually, and then it turned out that it's very closely related to group theory and what finitely generated but infinite groups do, and the two topics sort of grew together. And the next thing is that if you have a sequence which you say it's convergent, you think it's convergent, then you want to define a limit object, and this is called a graphing. It's a exact definition, it's a bounded degree Borel graph on 0, 1, so the edge set is a Borel set, the vertex set is just the 0, 1 interval, and there is a certain measure preserving property which is important, but I will not define it right now. But I would like to show you my favorite example in this area. So here is about Penrose tilings. Probably most of you know what they are. There are different definitions. Let's, for example, use the following definition. There are these two rhomboids, the white one and the gray one. And there is some rule that which edge can be glued together with which edge. So, for example, you cannot take two white ones and glue them together along an edge so that the two together form a larger rhomboid. So these are or paragram. So these according, so there are some minor rules how you have to glue them together, and then there is a fact that theorem that these two rhomboids they tie the plane. You can tie the plane with them, the whole plane, but you cannot tile it in any periodic way. So every tiling contains infinite amount of information because you cannot simply say that I take this and then I repeat it, as you would probably with most of the tilings that you can think of. So this is a Penrose tiling, and if you take larger and larger pieces of Penrose tilings, so then this will form that's a theorem, that it forms a sequence which is convergent in the Benjamin-Isham sense. So if you pick a random, and now you see why to pick a random point may be non-trivial. If you pick a random point from the whole, well, as long as it's finite, it's okay. But if you tie the whole plane, then it's not meaningful to pick a random point and look at its neighborhood. So you have to be careful with this definition because it has a countable number of points. However, it turns out that there are many Penrose tilings, and each of them converges. I mean, it's larger sequences, they converge to the same object, which is the following. You take a rhombic icosahedron, one of those classical polyhedra, semi-regular polyhedra, and you put it on, stand it on one of the vertices, and then you slice it across the other vertices. So you get these 5 pentagonal slides. And so this limit will live on these 5 parallel slides or cuts. And so these will be the vertices, and you connect 2 of these vertices if the connecting vector is just equal as vector to one of the 5 edges going out from the top point. So there is 5 possible connections. They all have the same length, but they have different directions. Now, if you look at these 4 pentagons, you can pick a random point from one of them, and then you can trace the connected component, and this will give you the whole plane, a Penrose tiling of the whole plane, and every Penrose tiling you can get this way. So that gives you a very nice definition of what's a random Penrose tiling and how to look at a random point of a Penrose tiling. So this is basically a reformulation of some old results of de Bruijn, but it's a nice one. So what do we know about graph limits just on one page? There are 2 extreme cases. You can talk about limits of dense graphs, and so that means they have a constant times n squared nodes, where n is where n is the number of nodes. And this is a well-developed theory. You can define global and local convergence, so convergence depending on different tests. You can define limit objects, they are called graphons, and it's a well-developed theory. Or you can talk about bounded degree graphs, which I sketched a little bit, and they have a deep theory, but it's still incomplete. For example, we don't know what are the possible limit objects there. Every limit can be represented by a graphing, but it's a famous unsolved problem whether every graphing is a limit, and that's equivalent to some classical problem of Gromov in finite, the sophicity problem of finitely generated groups, whether every finitely generated group can be approximated by finite groups, and that's a generalization of it. So this is a more difficult but also very exciting subject. And there is a middle ground, and there is work in progress, but it's very difficult, and I am not sure if it will ever finish, because the results are not terribly exciting, and at the same time rather difficult to obtain. However, that's not what I would like to talk about. So suppose we have a convergent sequence of graphs, say in the Benjamin-Isham sense. Now, if you have a graph, you study the graph by defining various structures on it. And what are these structures? For example, you take matchings. You want to match up the vertices by edges, as many as possible. Or you look at colorings, like in the 4-color problem and so on. Can it be colored with 4 colors? So that adjacent nodes get different colors. You can define flows on them. You can look at the adjacency matrix and the spectrum, so there are eigenvalues of these graphs. You can study the automorphism group of this graph, and you can also study matroids of this graph. Now, it is said that when you are giving a talk, especially to a general audience, and when you get to the first formula, then half of the audience will fall asleep. In a mathematical, with a mathematical audience, the word matroid plays this role. It is. I will try to explain what it is, and it's a much studied. There are monographs, many monographs on matroids. And they are indeed very nice structures. So what are these matroids? Let's go back to the work of the Czech mathematician Borůvka from 1926. And his task was trying to optimize the Czech electrical network. So of course, I mean, the simplest model is that you would like to define a cheapest network that will connect every city. And so we think of the cities as vertices of a graph, and an edge means some connection which is possible, geographically possible, direct connection between them. And all these connections have a certain cost. You can think of it as the length, but maybe it's a bit more. But they can all be computed or estimated. So for example, you are looking for such an object, so it's a tree that you would like to pick, a spanning tree of this graph with minimum length. And that's a problem. And he developed the greedy algorithm, which is a most natural algorithm to apply here. You build these connections one by one, or you point or you color it red one by one, and always choosing the cheapest, but of course you bypass those connections which don't provide anything new. So you always add edges which will make 2 previously unconnected nodes connected. So increases connectivity. And then there is a theorem. The algorithm gives the exact optimum. Now it turns out that this significance of this was discovered less than 10 years later in a general form by Hassler-Whitney and van der Waerden, so very important mathematicians who noticed that there are some very simple properties of these spanning trees or subsets of spanning trees, forests, let's call it. And they developed this system of axioms that there is a finite set, E, and I for independent, is a family of its subsets, which contains, and then the first 2 axioms are sort of trivial. It contains the empty set, and if it contains a set, it contains all the subsets of it. And the third, which is sometimes called the Steinitz exchange property, that if you have 2 sets and in this family and one is larger than the other, then you can pick a point which is in the larger but not in the smaller, so that you add it to the smaller and you stay in the set, so stay independent. And it turns out, as was observed, that there are several concrete examples of this kind of situation. Linearly independent sets in vector spaces is probably the most natural example, or most everyday example, but also algebraically independent sets over a subfield. So instead of linear independence, algebraic independence will have exactly the same properties. Or, coming back to Borowska's work, cycle-free edge sets in a graph also have these properties. Okay, that's nice that they have these properties, but the point was that it turned out that many, many deep facts can be derived from these properties. I will mention later a couple of them. Now, however, first I would like to introduce the notion of a rank function. So if you have a matroid and then you define the rank of a set, just think of the linear independence. So a rank of a set is the number of the cardinality of the largest independent subset. And then this rank has, again, some trivial and one non-trivial property. The empty set has rank 0, it's monotone increasing, it's bounded from above by the cardinality function, and the rank of the union plus the rank of the intersection is less than or equal to the sum of the ranks of these two sets. And this is called submodularity, and this will be somehow a central topic in the rest of my talk. And now here, why am I excited about this topic? I would like to tell you to me, very, very surprising tale of two communities. So one is study of submodular set functions on finite sets, and the other one is study of them on infinite sets. And I just want to mention that about a year and a half ago, we began to think about this with a number of very talented young guys at the Rényi Institute, and we really found that there is really a surprising how unconnected these two cities or two communities were. So so here is a submodular function. The rank of the intersection plus the rank of the union is bounded above by the rank of one plus the rank of the other. And for some reason, this formula got distorted when we looked at it. It's always a danger when you use PowerPoint. So to begin with, I showed you some examples where this rank function is defined on finite sets. Here are some examples of rank functions defined on, say, subsets of the 0-1 interval. The supremum X as a set function is submodular. The square root of the Lebesgue, of course the Lebesgue measure is submodular, but the square root of the Lebesgue measure is also submodular. In fact, any concave function of the Lebesgue measure is submodular. Or the Lebesgue measure of the closure is submodular. These come up in all sorts of situations. Now, the infinite version of, as far as I could trace, first came up in a work of Choquet in 1954. And when I say work, that's really work. It's a paper of 160 pages. So, and it's a very, very condensed paper on 160 pages. It's a beautiful paper. It's a really seminal paper, almost like a book, a little book. So what he was interested in the following question. Take a domain in R to the D, open domain, say bounded for simplicity. And then for every subset X, you would like to define its electric capacity. That would mean how much electric charge can you put on this subset, and you require that outside the domain the potential should be 0. And then the question is, how large will be the potential? I mean, the maximum will be somewhere on that subset, of course, and then it goes down. So actually, the question you ask in the converse way, you say that we put charges so as this potential should nowhere exceed 1, and then the question is, what's the maximum amount of charge you can put on this set? And this he calls the electric capacity, or just the capacity of this set. Now, this can be computed for simple sets, like if you take a square or a circle inside the domain, then it exists. And it was an open problem. How far can this definition be extended? Can it be extended to all open subsets or all closed subsets? And he proved that it can be extended to all Borel subsets, which was conjectured, and in fact, he proved that it can be extended to analytic subsets, but for me, the Borel sets will be the important ones. So he proved that it can be extended, and then in this paper, he introduced a number of powerful techniques, one or two I will mention. But in the meanwhile, and then actually a little earlier after the work of Whitney, which I already quoted, there is also, I should mention, the work of Richard Rado from 1942. And sorry, the strange thing there should be a phi. So here is what, and I would like to mention, I mentioned Rado's work because he introduced a submodularity which is different from the submodularity of matroids. So you look at a bipartite graph, and in one class, say the bottom class, you pick a subset X, and you count how many neighbors does it have in the other class. And then the number of these neighbors is a set function. For every set downstairs, it has a certain number of neighbors. It turns out that this function is submodular. And Rado used this submodularity to prove theorems about bipartite graphs and systems of distinct representatives and so on. So some results in some classical, nowadays it's sort of very well-known results in graph theory. So this is not a that doesn't come from a matroid. It's a different object. Now, Choquet's work was continued. I want to mention that there are two important monographs that actually describe this. It's sometimes called non-additive integral, sometimes called strongly subadditive. Why is it integral? I will come back to this in a minute. Now, Whitney's work was followed by work on matroid theory, also by Rado, Todd, Edmonds, and many other people. But let me just point out that there is the famous Max-Fromin-Cut theorem, which is really the theorem which started the field of combinatorial optimization, I would say, or its applications. And in this Max-Fromin-Cut theorem, there is the cut capacity function. So for every set of points, you look at the capacity, say in the simplest case, just the number of edges that connect this subset of points to its complement. Now, it turns out that this function is submodular. And again, we are getting a more general function because that's not even increasing. A larger set may have a smaller boundary. And it turns out that this is submodular, and the Maxwell-Cut theorem was generalized in 1,000 ways, and the submodularity of this function plays an important role in many of these generalizations. It is a funny coincidence that two basic examples in the continuous and in the discrete setting, they are both called capacities, although I think they are probably not the same thing. But I don't see any connection other than this coincidence. Now, okay, so let me talk about one thing that Choquet introduced. So let phi be an increasing submodular set function on the Borel sets. This is, the examples I showed you are all like that. And now you take any Borel, say bounded Borel function f, then you can define phi hat of f, or as the following. You look at the level sets of f greater than or equal to t. This all have this set function phi has a value on them. And because phi is increasing, this value is decreasing because these level sets are decreasing. So it's a decreasing set function. It can be integrated, say f is non-negative, and then we integrate it from 0 to infinity. But for large t, since f is bounded, for large t you are integrating 0, so it doesn't matter. So the integral exists. And this is denoted by phi hat of f. Sometimes this is denoted by integral f d phi. And this is what's called the nonlinear integral, because it's nonlinear, but it's sort of other properties. But I don't want to confuse you with this. I just wanted to explain the title of Denneberg's book. But f maps to phi hat of f is a functional on the space of bounded Borel functions. And this is a convex functional, as Choquet proved, and that has very important applications, that this is a convex. It's very, once it's convex, it's very nice. Now, in the discrete world, there is a notion of a similar extension, which is sometimes named after me, although I have to admit that it was discovered, about 30 years later, and it's a very special case in some sense because it concerns finite sets instead of Borel sets. And it can be defined, can be computed for every x by decomposing this set x into a linear combination of indicator functions of a chain of sets, and then just apply linearly the phi. And this phi hat, and it is a convex function. So why do I mention this very special and case so much later? The important thing is that increasing is not a condition here. And if you think about, okay, so you have this function, you extend it to a convex function. This is a convex function, this phi hat. So you extend this phi, which is defined originally on subsets, so 0, 1 functions. You extend it to the whole unit cube, say, or all non-negative vectors. It's very important it's an important algorithmic task to minimize a submodular set function. Max flow min cut, you have to minimize the cut. For example, I mean, it's the simplest case, but there are many other applications. Now, once you extend it to a convex function, you can pull some methods from continuous mathematics how to minimize a convex function, and you can apply it here. But if you think of this example, this function is not monotone. So this whole minimization problem is meaningless for monotone functions. So it's important that it's not increasing. So what happens to the increasing condition in showcase extension? And I'm actually surprised that we have discovered that it's not needed and that it's non-trivial to prove that it's not needed. So this integral, which I had here for increasing functions, exists, of course, because it's an integral of a monotone function. But if phi is not increasing, then this is not a monotone function. And so you have to work to prove that for submodular functions, you can drop this increasing condition. And it still works, and it's still a convex functional. So this I would say is sort of a first example of a cross-fertilization between the two areas of discrete and continuous submodularity. Now, here is the greedy algorithm. This is just recalling Borufska's work. And this generalizes to all matroids, so it's really... and for an increasing submodular function, again, the earliest reference I have found to this fact is from 1979 by Sipos, who proved that if phi is an increasing submodular set function on the Borel sets of 0, 1, and for simplicity assume that it's 0 on the empty set, then there exists a, okay, what is this charge? A finitely additive measure, alpha, on the Borel sets, which is less than or equal to this phi on all sets, but agrees with this phi on every beginning section. Now, if you want to find somehow a largest alpha in this sense, then and you think of x as time, then it means you start from left, and at every particular time you will put into this measure, it's kind of a measure, alpha, as much as you can, namely phi of that same set. And the point is you can do that, so there is this. So the greedy algorithm, which means you pick at every time as much as you could up to that point, this remains valid in the infinite case, and in fact it's sort of another known result there. Now let me talk a little bit about this matching problem in graphs. So this is a classical problem. You have a bipartite graph, and you would like to find the maximum number of disjoint edges in a graph. I would like to point out that the greedy algorithm doesn't work in this case. So you can pick unfortunate choice, make unfortunate choices which you cannot finish. But the problem is well solved for a long time. Well solved meaning there is a polynomial time algorithm to find the optimum. Now, let's look at an infinite version of this problem. So in the finite case, you can translate the problem into a matrix problem. And in fact, the first solution problem came from Frobenius in the form of solving this matrix problem. So the matrix problem is that you have matrix where certain entries are zeros, others are non-zeros or ones, and you would like to find, say in the simplest case, you want to find as many ones impossible, these are the red edges, so that no two of them belong to the same row or column. Optimally, you would like to pick one red one from each row and column. So this is the perfect matching problem. And okay, so what is the analog infinite problem? You have the 0, 1 square, so the unit square, and R is, say, some measurable or Borel subset of the square. And the question is there a measure on the Borel subsets of R? So you are looking for a measure whose marginals are the Lebesgue measures on the sides. So it's a coupling measure, coupling two copies of the Lebesgue measure. But you require that it's supported on this set R. The question is, when does this animal exist? And in the discrete case, there is a theorem of Frobenius and Koenig. Frobenius was the matrix version, and then Koenig generalized it, and it became a big theory. And it's called the marriage theorem, that if you have a bipartite graph, this bipartition as before, and then it has a perfect matching, if and only if the two sides, of course, have to have the same cardinality. And kind of going back to Reido's notion, so for every x on one side, the number of neighbors should be at least as large as the cardinality of x. That's necessary and sufficient. So what happens in the continuous world? There's a theorem of Strauss, also fairly old, which says that if closed subset, then, and you are looking for this measure with marginals which are equal to the Lebesgue measure, then such a thing exists if and only if for every Borel subset of 0, 1, you look at the neighbors, meaning you project it up to R and then project it down on the other side, and this should increase the Lebesgue measure, or not decrease. It's very trivial to see that this is a necessary condition. The point is that you want to make it necessary and sufficient, and it doesn't work on R's. I am cheating here because, or at least misleading you, because Strauss's theorem is more general than that. But closed is sort of probably the simplest condition, non-trivial condition, which you can impose here. So I just wanted to formulate it like that. But here, if R is not closed, then let's take one of the simplest open sets, which is everything below, strictly below the diagonal. It satisfies the condition. It's very easy to see, but you cannot define a coupling measure on this open set, supported on this open set. Homework exercise. So so can we do something? What is this condition on the bottom good for? And so again, let's go back to the finite case. The marriage theorem can be derived from a general theorem on matroids. That's the matroid intersection theorem. That's one of the really baby applications of matroid intersection, but the matroid intersection theorem is a nice theorem. It says that if you have two matroids on the same underlying set, but they can be, one can come from algebraic independence, the other can come from graphs or whatever, and you are interested in a maximum cardinality of a set that is independent in both, then you can get this maximum as the minimum of the first rank of a set plus the rank of its complement minimized over all subsets of E. of the underlying set. Okay, so that's an important theorem. And the question is, how does it look in the general, in the infinite case? And indeed, there is a submodular intersection theorem. It says that if you have two increasing submodular set functions, not only matroids, but two increasing submodular set functions, and you want to maximize, what is it? In this formulation, you take alpha, which is bounded by, it's below both of them, and which is finitely additive measure, and you want to maximize the total measure, then you get exactly the same formula as in the finite case, except that you have to put infimum there because the minimum is not necessarily attained. Okay, so that's a generalization. What happens if we try to apply this to Strassen's situation? So, and the theorem that it gives is the following analog of the Merit theorem. So we have a R, which is a subset of the unit square, and we want to find now a finitely additive measure on the unit square, whose marginals are the Lebesgue measure. So the marginals are countably additive, but the set can only be required to be finitely additive. But then this condition that we have looked at several times in the last minutes, this condition, lambda of R of x is greater than or equal to lambda of x, is necessary and sufficient. And then some basic measure theory tells you that if you have a charge here, then it's just some standard hocus pocus with Banach spaces, which will tell you that then you have also a countably additive measure, which only slightly gets out of this set. It only extends its support to the closure of this set. So this way, this implies the version of Strassen's theorem I told you, but this gives this condition. Now, finally, I would like to talk a little bit about related to convergent sequences of graphs. So I told you that once we have some sequence of graphs, we have a graph, we are interested not only in the graph, but various special structures on it, including the matroids, automorphism groups, and so on. Now, which sequences of submodular set functions on finite sets are convergent? What is the limit object? So we have a convergent sequence of graphs. Each of them has an associated matroid, namely this Borufka, the spanning trees and their subsets. What is the limit of this sequence of matroids? Does it have any relationship with the limit of the graphs? So, sorry, I have to make some definitions here. So, we look at the Borel sets on 0, 1. Could be on any other Borel space, of course. And we have a submodular set function on them. And now we look at a map from 0, 1 to the first k element set, say the set 1, 2, and so on, k. And this should be a Borel map, so which means that it's the same thing as saying that we partition J into k Borel sets. And then there is the phi. If phi is defined on the Borel sets, then under this map it has a push forward. This means that a set of subset of 1 through k will have a function value by looking at its inverse image, and that has a function value. And this is also a submodular function on this finite set. And we denote by qk of phi the set of all these submodular functions. We call it a k-quotient of phi. So qk of phi is the set of k-quotients. And now we say that a sequence of submodular functions, on each of them is on a finite set, but on larger and typical larger and larger finite sets is convergent. If for every k you look at the set of its k-quotients that sits in the 2 to the k dimensional, finite dimensional space, and if this sequence is convergent in Hausdorff distance, what does it mean? It means that if there is a quotient which is of 1, then if you go far enough, then in the other one, there will be a quotient which is almost the same. For every epsilon, they only differ by epsilon on any subset of the first k integers. So if we think of this qk phi as the test or the statistics of this, then this means that they are less and less distinguishable in terms of the statistics. Okay, so and they converge to phi. I mean, you can define this also for an infinite case, phi, qk of phi, and if the qk of phi n converge to qk of phi, then we say that the phi n converge to phi. Now it turns out that this convergence has many nice properties, and one main theorem is that if a sequence is convergent, then it does have a limit object. So every convergent sequence converges to some phi, which is a submodular set function on the Borel subsets. And it turns out that the proof of this uses Choquet's main theorem of the big paper. So somehow, okay, the measure theory strikes back, because for this problem which comes from graph theories trying to understand the structure of large graphs, we could use this classical theorem which came from mathematical physics. And now okay, so this is fine. So there is this limit object. Does it have any good properties related to graphs? Now it turns out that for a finite graph, okay, so you have the rank of a set X is the maximum size. That's the old definition of a forest. So it means a cycle-free subgraph, and that can be expressed as the number of nodes minus the number of connected components if you only keep these edges. That's a simple identity. Now let's normalize. So we divide it by the total number of nodes, and then instead of denoting it by r, let me denote it by rho. So rho g of x is 1 minus, and now it turns out that this number of connected components divided by the total number of points is the same. Again, a very simple identity. It's 1 over the following quantity. You pick a random point, u, in this subgraph Vx. It has a connected component. You look at the size of this connected component, the number of its points, and take the reciprocal and the expectation of that. Just simple identity, nothing deep in that. But the point is that this gives you, first of all, sort of a nice algorithmic way with a randomized algorithm to compute this. And second, that this generalizes to to those graphings that I was talking about, because graphings was kind of graph on the 0-1 interval. Now, you need to prove things, so every Borel subset of this itself is a graphing, and then you pick a random point and it will have a connected component, which may be infinite or maybe finite. If it's finite, then you take 1 over the size. If it's infinite, you can still take 1 over the size, it will be 0. And then you take the expectation of this, because from the 0-1 interval, you can pick a random point. Again, that would not work if we only looked at countable infinite graphs. So you have to be able to pick a uniform random point of the vertices, and then you get this. And there is a theorem which I just have to sort of close things off, that if there is a sequence of finite graphs with bounded degrees that converges in some sense which I am not going to define, it's locally, globally to a graphing G, then the corresponding rows also converge. So in other words, for a graph sequence which is convergent in this sense, the corresponding submodular functions are also convergent. This made my young postdocs, graduate students and postdocs, very enthusiastic, and they have worked out all the nice theory about this matroid of a graphing. This sort of shows that it justifies that you look at this notion of convergence, and then it indeed reflects the convergence of graphs. Thank you for your attention.
Thank you very much. It was very exciting. I personally was excited by the fact, that you used, which I didn't expect, result, Shock capacity theorem, that also some people in Krakow have used, working in a completely different area, potential theory and pluripotential theory. If I may start a question, I have a question myself first one. So you mentioned this Penrose tiling. Tiling, sorry. And I think I read like a year or two ago that they found out, so this consists of 2 regions that you can tile the whole plane, and not in a periodic way, but that they found out 1 region that you can do it. Yeah, is that right?
Yeah,
confirmed,
yeah.
Right?
I also, that's the way I remember, yes.
Yeah, okay. So I remember.
But I don't know whether that has a limit object or not.
I see, okay. Okay, so are there any other questions? Yeah, please. Should I ask? Maybe.
My question is about various limits that we have in this talk. First of all, when we have saying that something in the limit is equal to something like that, we have 2 questions. Limited what sense that you say what you want explained, and second, how fast this is approaching this limit. At least what when we on R, we know what we mean fast approaching. At studies and intuitive sense, can we have any intuition in this more abstract limit of convergence graph? How fast this is approaching? Thank you.
Thank you. So I indeed did not define. I think I defined in here for this that what it means that phi n converges to phi.
But I don't know how
Oh, I am sorry. It's I should have defined. So there are two subsets of Rn, and the Hausdorff distance is the smallest epsilon, for which it is true that for every point of one, there is a point of the other at distance at most epsilon. So, yeah. Now, how fast this convergence is, I don't know, and also about the others which I did not define, about dense graphs and sparse graphs and so on. There are lots of open questions about how fast this is. It's not even clear how you measure it, but just a convergent sequence can be converged very slow or very fast, but there are certain special sequences which should converge fast, but I mean, a famous unsolved problem is whether if you take a random D regular graph, so D is, say, 5. So you take a graph where every degree has 5, and you take one randomly out of all of those. So there's a finite number of them, and you pick one at random. And you do this for every number of nodes, then this sequence should be convergent well, in this local global sense, but it's not known to converge. So that's that's a famous unsolved problem.
Okay, yeah, there was another question.
Thank you for the lecture. You mentioned that submodular functions can be integrated even if they are not increasing. Can you please give some intuition why?
So submodular functions can be
integrated.
Oh, yes. So if instead of having an increasing function, you have the difference of two increasing functions, then it can also be integrated. And for this, it's enough that the phi can be represented as the difference of two increasing set functions. And now you can prove that every submodular function can be represented as the difference of two increasing, but not necessarily submodular set functions. Just a few weeks ago, one of my students found a counterexample that they cannot be required to be submodular. Finite case, they can be case, what is, yeah. So, but submodularity is an important property to use in the proof that they can be decomposed this way.
Okay, is there? Okay, there is.
Sorry, so I don't know whether it is possible to come back to some of the previous slides since the screen has disappeared, but okay, maybe I will try to.
Which one?
Okay, but still.
Oh, it's yeah.
Okay, so my question is about this example of this 1 by 1 torus. I don't know, what do you mean by that? 1 is the length of the side of the square, yes?
Yes.
So it's a two-dimensional torus, yes? And the relation is that we identify 2 points if...
No, it's the square in which the upper edge is identified with the lower edge and the left edge is identified with the right edge.
Yes.
Topologically, this gives a torus.
Yes, and then there is alpha.
Yeah, and so alpha is a length, an irrational number, and 2 points I mean, for every point, I can go up by a distance of alpha and connect it. Maybe while I'm going up, I jump around and I already come back from the bottom, but nevertheless, I walk a total distance of alpha and I connect it to that.
So this is the same as taking two copies of a circle divided by the action of z, where the action is rotation of the angle of alpha, yes? Is it the same?
Yes, I think, yeah. So you take two copies of the circle, yeah, and...
Okay, thank you.
Okay, I cannot see any other questions. So let's thank speaker again, László Lovász.
Thank you.